Okay, so following straight on from that, we have Wentao Li, who's also at Lancaster and also one of the highlight postdocs, talking a bit more about ABC, so on improved convergence of regressive adjusted ABC.
Okay. So after post talk, I would like to talk more about the ABC convergence. So firstly, I would like to talk why we want to improve the standard ABC algorithms. So the cost of ABC mostly comes from the simulation of the summary the pseudo data sets, and the size of the simulation cost is proportional to. So suppose we want an output size is capital N 0, and we want and in the simulating algorithms, the acceptance probability is a P accept. Then the total simulation cost of ABC is proportional N0 times small n, the size of data set, divided by the acceptance probability. Okay. So what we would like to know is that whether ABC can be accurate, that with the acceptance probability fixed when we increase the data size. Because if as the data size increases, in order for ABC to work well, the epsilon need to go small, and the worry is when the bandwidth goes small, whether we need more and more Monte Carlo samples to get this accurate ABC estimate. So if the acceptance rate can fix when n goes to infinity, then which means the cost of ABC can scale linearly in the size of the data set, right? Where n0 is fixed and can scale linearly with n. Well, if the acceptance rate will decrease to 0, will decay to 0, which means we will need more and more Monte Carlo size for the ABC, which means ABC is very expensive to apply in a large data set. So the summary of post talk revealed two problems of standard ABC. One is that it's more difficult to estimate the posterior uncertainty than to estimate the posterior mean, because for the posterior mean, you can asymptotically you can get accurate posterior mean with bandwidth larger than 1 over square root of n, but for the posterior uncertainty to accurately estimate it, the epsilon can only be small o, 1 over square root of n. That's shown in the limit distribution of in post talk. So that's one thing. The other thing is when the posterior uncertainty is accurate, when we use the epsilon is small o, 1 over square root of n, then we will see that later that acceptance rate will unavoidably degenerate to 0. So that's the two issues with standard ABC. So let's see a very simple example. Suppose we just want to estimate the parameter of a univariate normal distribution, and the mean function is a cubic function of the parameter theta. And in order to get the highest acceptance, so we propose the parameter values from the posterior itself, which has the highest acceptance probability among all reasonable proposals. Then we check the acceptance probability needed to achieve a certain accuracy level of ABC. The left one is for estimating the ABC posterior mean. Right one is for estimating posterior variance. Well, in the experiment, the data size ranges from 50 to 10,000, which is on the x-axis, and the y-axis is the acceptance probability. So you can see that for estimating the posterior mean, that you can keep as data size increases, you can keep the acceptance probability fixed and even close to 1 in order to get the accurate estimate. But for the posterior variance, only for small n, that you can get a large acceptance probability. But other than that, if n increases, that keep decreasing close to 0, which means in ABC that you need to reject most of the samples in order to get an accurate uncertainty estimate. So this is for trivial examples, but shows the problem of standard ABC. So why this is the case? That this is essentially is because the optimal epsilon, the epsilon that can be negligible is too small. So think about this. So think about you would accept Monte Carlo samples in this red circle, which is centered at your, you accept around the observations with the radius small or 1 over square root of n, which if you accept in this sample, your estimate will be accurate. But when you simulate the pseudo data set, most of the pseudo data set will fall in this black circle. So just think about you simulate the pseudo data set from the true parameter values. And the distance of your pseudo data set to the true parameter values is capital O or 1 over square root of n, right? Which makes the radius of this black circle much larger than the radius of the red circle. So when you take simulations, most of them will fall in here. As n goes to infinity, the red circle becomes smaller and smaller, and compared to the black circle, which makes your acceptance rate region, this acceptance region, most of the samples will fall out of the acceptance region. And so your Monte Carlo efficiency just degenerate to 0. So that's what this formal result says, that as n goes to infinity, if epsilon is small or 1 over square root of n, the acceptance probability for any proposal distribution will go to 0. So no sampling algorithm will help, and which means the computation cost will need to increase substantially with data size. Therefore, the standard ABC algorithm is not efficient. So that's the problem of the standard one. Before talking about how to improve this, so I would like to restate the convergence of ABC posterior result that just stated in the post talk. Well, mainly for you to familiarize some notations that I can use later on. As I said before, the result appear in these two papers, and well, this result is for the the 3 type of limit distribution of ABC posterior distribution. So the limits will depends on the relative rate of square root of n and epsilon n, and here we just consider the dimension of summary is equal to dimension of the parameter, just for the simplicity of presentation. But everything holds for d larger than p, just for more involved form. So well, the result this is just restated. So when epsilon n square root of n times epsilon goes to some c is less than infinity, then we let t be the scale and center theta, and consider the ABC posterior of this t. Then we will have 2 forms. When epsilon is much smaller than 1 over square root of n, is epsilon very small, then we get back the true limit, the limit of the true posterior based on given the summaries. And if epsilon is in the same order as 1 over square root of n, then we will have these convolution forms, which inflates the uncertainty of the true posterior variance. If epsilon is much larger than 1 over square root of n, then the scale will change to epsilon n to the -1. This is the proper scale, which means even the rate of convergence will decrease to epsilon n. And then the ABC and also the ABC posterior will have the limit form, which depends on the shape of the kernel density instead of the correct normal shape. So which means when epsilon is too large, then both the convergence rate and also the shape will be destroyed. So therefore, the epsilon n is equal to small o 1 over n. Only this one is negligible. And so I just state a more explanation of why this is the case. That so the ABC posterior of t, it can be written as a convolution of the true posterior with the kernel density, because you simulate the summary, the pseudo data set around the true the observations, and then you average all the true posterior given the summaries, and the S is coming. You have this acceptance probability in here. So when we try to get the asymptotic result, we use the asymptotic result under model specification, because this posterior, the likelihood of this posterior is the F is the model likelihood, but the S doesn't have besides containing the randomness of the data set, it also contains the randomness from accept to reject, which makes your likelihood, the density of S is not only contain the true likelihood, it also contains the acceptance probability, which makes this is not the posterior, it's not so which makes the likelihood on the side that this posterior is not the density of S, so which has this model specification problems. So we use a result in Klein and Wentao in 2012 to get this leading term of the posterior given the summaries. So as posed as before, the variance doesn't depend on the summary. It doesn't depend on S, but the mean will depend on S, which makes the issue of 3 different limiting distributions because of dependence. So the form of mu S contains say 2 parts. One part is the common part, doesn't depend on S. The other part depends on the difference of S minus S of. Beta 0 is just the linear transformation from the space of S to from the space of S to theta. And this common part, it can show that it's equal to, well, it's approximately equal to the ABC posterior mean. So the mean, so for each of the pi theta given S, this mean is equal to the ABC posterior mean plus some part depend on S. Okay, and so and then by using these three things, we can get the ABC posterior distribution that's for the scale theta, scale and center theta, where we just in the mean you just remove this common part and then times the scale square root of n, so which makes your mu s divided by minus the common part and everything times square root of n. So that's how you get this convolution form here. Comes from convolution here form here. And so the mean part here depends on the product of square root of n times epsilon n, and so it totally depends on how these rays converge. And so if this one goes to 0, well this normal density doesn't depend on v, and so there's no effect of the epsilon inside this limit distribution. If this part depends on, if this part doesn't go to 0, everything it depends on the v, then you need to take this convolution form. And if this epsilon is too large, this one goes to infinity, then after we change the scales, this convolution form becomes like this, and the rate of the variance is 1 over n times epsilon square. And so because this part goes to infinity, so this normal goes to a point mass, and so which gives you the final distribution, just a kernel function. So you have three forms. Okay, so we can see that the problem is caused by the dependence of v in this convolution form. So now let's talk about the regression corrections. Yesterday in Carrie's talk, she mentioned a bit about the regression corrections. So as we see, the problem of ABC is because it's caused by the fact that you have the non-zero epsilons, and then remember that in your output, besides the parameter values, you also has the information of the distance of the simulation to the observations. So as if the distance is large, then which somehow means your parameter value is not that good. If that is small, which means your parameter value is good. So it's natural to think about just combining these two informations, use the information of the distance to adjust the value of your parameters. This motive, so Bormann et al. In 2002, the paper which creates the terminology of ABC, it proposed the linear adjustment to theta. So the adjustment is very easy. It's a post-processing. After you're getting your ABC output, you just adjust your parameter values with a linear transformation of this difference. And the beta hat is estimating using linear regressions. That is the slope of fitting the linear model of with response theta and the predictor s minus s op. So it might be easier to see how it works in these graphs. So on the top two plots, this is the output of ABC, and so you have theta and y-axis is s minus s op. So the right plot is the estimate of the posterior, which has a bit of weird shape that you have bimodal here and doesn't look quite well. Well, this is because you are existence of the epsilon. So in the left bottom plot, that after getting this ABC output, you just fit the regression line, which is the red line here, and then for each of those black dots, you calculate its regression residuals, and then add these regression residuals to the predicted values on s minus s op equal to 0, which is the dashed line. So we add these regression residuals to this dashed line, and then give this red dot. Okay, so after you make this, so this is equivalent to just construct this linear adjusted theta, and so then you get this shrinkage effect of those black dots, shrinkage to the red dots, and then you use this red dot to construct the estimated posterior, which gives this nice looking sharper posterior estimate. Okay. So this is just the regression corrections, which is simple, and it has some benefits. First is it shrinks the accepted theta to the ABC posterior mean, we just saw, and also it reduces the bias of ABC point estimate. That is the main motivate the thing Beaumont mentioned in this paper, and also reduce the ABC posterior variance. Well, as you see here, the variance the variance of the approximate posterior is also decreased. Well, this can be seen just by standard control variable argument. Okay, your variance of theta star is always smaller than variance of the theta. So because our previous worry of the theta only is estimated posterior variance overinflated the true posterior variance. So this gets reduction, which is good. And the remarkable thing is that both 2 and 3, the reduction given in 2 and 3 asymptotically is the exact amount needed to correct the errors in ABC. And the formal result is very straightforward. When considering the asymptotic result of theta star, so we consider the theta star is theta minus beta epsilon hat times the s minus s op. So in order to obtain the asymptotics of this theta star, so there are two sources of randomness in theta star. One is coming from the randomness of your data set. The other part is the randomness coming from your Monte Carlo sample. All right, these are two parts. Because these two randomness are independent, so we consider the asymptotics of both of these two separately. So there are two steps in getting the asymptotics of this thing. So first we consider the ideal linear coefficients beta epsilon minimizing the expected square loss. And then we consider the impact of the finite sample estimate of beta epsilon. So when with the ideal linear coefficients, we let theta optimal theta to be the theta minus beta epsilon s minus s op, and the result is very straightforward. If epsilon is equal to small n to the negative 3/10, which is larger than n to the negative half, okay, so which means epsilon n can be larger, and then consider the scale, the scale and center theta op, and the ABC posterior will converge to the distribution with just the correct density, okay, and also the ABC posterior mean also converge to the correct density with the correct convergence rate. The issue of the ABC point estimate is that when d larger than p, the asymptotic variance is not I theta 0 as shown in post hoc. It's something that's smaller than is smaller than I theta 0 because of the problem of epsilon. So regression correction also corrects the problem in the ABC posterior means. So this holds for d larger than p. So why? So how this result holds? So so follow the similar intuition before that ABC posterior mean for this theta star can be written as also in this convolution form, and it just differ from the previous convolution form that you have an extra adjustment term in here. Okay, previously it is pi theta given s. Here it becomes pi this theta plus an extra term here. And asymptotically, this posterior also it has a normal leading term, which the variance doesn't depend on s. Now the mean depends on s, but now you also have an adjusting term minus beta epsilon here. And remember the form of mu s is a common part plus a part that depends on s, which with the linear transformation matrix beta 0. So now the ABC posterior for the regression corrected theta now becomes this convolution with the mean. So previously the mean is this square root of n times epsilon n times the beta 0 times v. This is the previous convolution for the ABC posterior is like that. Now it becomes beta 0 minus beta epsilon. Okay, we have an adjustment here. So it can be shown that the remainder, this difference, it converges to 0. Or this has just very simple derivations. But more importantly is that this remainder has the order of small o1 over square root of n times epsilon n. This thing goes to 0. But this needs some extra efforts of getting this order. But that's the more important thing. So which makes everything works, and this thing goes to 0, and find the limit becomes anti-0 with the correct information matrix there. Now that's symptotic with the ideal linear coefficient matrix. Now what's the impact of the finite sample estimate of beta epsilon? So for the theta star, which include the finite sample impact, if so, the conditions are similar. So the condition of the epsilon is the same. The thing changes is the distribution now becomes a bit similar to the previous convolution type of form. But what's matter here is the mean now has the rate of 1 over square root of n, capital N, which is the size of your ABC output. Okay, the size that you use to estimate your coefficient matrix. So which means this convolution form is like your mixture of your correct posterior limit with the density of a random variable has the order of 1 over capital N, 1 over square root of capital N. So with the capital N is a reasonable size, this mixture can somehow is negligible. This is close to 0, and you have this limit of your correct posterior back. And therefore, even with the finite sample estimate, the impact that epsilon n is small o n to the negative 3 over 10 is negligible with reasonable size of capital N. So this also needs a bit work to get it done. So here's the intuition. So when you consider the finite sample estimate, the only thing changed in the previous convolution form you saw is just the beta epsilon is replaced by beta epsilon hat. Okay, as I said before, if there's no hat, then this thing goes to is a small o1 goes to 0. Now we consider the impact of this hat. So we just only need to consider the order of square root of epsilon times the difference between the beta hat and the beta. Just so where we can show that the beta hat minus beta can be written as this covariance times this inverse of this variance. This is the finite sample covariance between S and the theta star, which is the optimal beta epsilon, times this inverse of this variance. So now we want to get the order of this thing. Okay. So there are two. Still, because there are two sources of randomness, we consider small n goes to infinity and capital N goes to infinity. So on one hand, because the S contract, we know the contract, the convergence rate of S and theta star optimal. So because S contracts at the rate epsilon n, because that's how you accept S, and if theta star optimum contracts at the rate 1 over square root of n, so we just write this difference in this form, which inside we normalize the S and also the theta star, so we have this S minus S epsilon divided by this, and theta star minus its mean divided times the epsilon square root of n. So for this term, we have shown previously in the limit that this is goes to this is the correct scale, and also this one is a correct scale, and so finally we get the rate term in front, which is square root of n epsilon n. So when fixing capital N, so the capital N is fixed and let n go to infinity. Well, this difference has this 1 over square root of n times epsilon n. Okay, it's capital, it has this order. Well, on the other hand, that when the capital N goes to infinity, we keep the small n fixed, the data size fixed. That this covariance, it converges to the covariance of S and theta star under the ABC posterior, and this covariance is equal to 0. Okay, so which means this in this formula that this covariance goes to 0. So which makes this covariance being the order of 1 over square root of n. So therefore, this difference has the order of 1 over square root of n times epsilon n times the 1 over capital square root of n. So which makes the dependence on V here is just in the order of 1 over capital 1 over square root of capital N. Okay. So we have shown that epsilon n can be negligible up to the order of up to the rate that is much larger than 1 over square root of n. Okay. Now, what does the impact? What's the impact on the acceptance region? So now consider we propose a parameter value from location scale family, which is easy to analyze, and also is general enough because it's the building stone for important sampling, sequential minimum sampling, many of these sampling algorithms. So we consider the proposing parameter value from this family, and that's the previous problematic acceptance region thing. So now, because now we can enlarge this red circle because epsilon can be larger. So if we enlarge this red circle to say capital N 1 over square root of n, which makes that when we take samples, that the acceptance probability now doesn't need to degenerate to 0. And even more, because the epsilon n now has a rate larger than 1 over square root of n, so we just can increase the red circle to the circle much larger than the black one. So then, which means if you take samples, then most samples fall in the black line can all be accepted. And this is for the proposal. The proposal has a variance of 1 over square root of n here. In many cases, the proposal we learned that is not as good as the posterior itself, so the variance might not be in this form. But because the order of epsilon n, we can also enlarge the sampling regions of this in this black circle. We can also allow the epsilon to be larger than 1 over square root of n, which means your proposal distribution can be worse than posterior, as long as it's not too worse, as long as it has the variance that in this rate. So, so in practice, what we need to learn is just an appropriate posterior value for the proposal variance, and then we use this common. So in ABC, there is a common way of getting the value of the epsilon. Okay, well, in order to know the value of the epsilon, or sometimes people need to know the meaning of the distance in order to get appropriate values. But after we fix a proposal distribution, then you can just generate samples and then accept a fixed proportion of the simulations, and then use the quantile of your distance as the epsilon. Okay, that's the kind of fix. You fix the proportion of the acceptance. So now the result is, if you assume the proposal can cover the two parameters, and if we have a good enough proposal, which is with this sigma n, then in this fixed proportion acceptance type of ABC algorithms, that we can let the acceptance proportion converge into 1, and then the resulted epsilon is still fall in the negligible region. So therefore, now with regression corrections, the ABC can be efficient. So finally, is non-Gaussian distribution. So this is a univariate example, but it shows how much improvement you can get from the regression corrections. So the observation follows this GNK distribution. The distribution is defined by the quantile function, and the quantile function is a transformation of the normal quantile because it's defined this way that you cannot write out the likelihood. So this is a benchmark example usually used in the ABC literature. So the likelihood is highly non-normal. So it has a heavy tail and is symmetric. So it's still to be checked the performance of ABC similar to the previous example you saw, that we check the acceptance rates that needed to achieve certain accuracy levels. And the x-axis is the quality of the proposals. C is the scale of the proposal variance. The larger C, the most dispersed the proposal is, the worse it is. So left is for estimating the posterior mean. So you can see that it doesn't make much difference. The dashed line is for the regression corrections. The solid line is without that. So it doesn't make much difference. But when you opt to estimate the posterior variance, that you can see that still most of the you need to reject most of the samples when not using regression adjustment. But here it can be even close to 1 if you use the corrections. Okay. The improvement here, most of them are over order of magnitude, over 2 order of magnitude. Okay. Summaries. So we provide the sufficient conditions for ABC to accurately estimate posterior distribution. So with the unadjusted ABC algorithm, so it is not efficient for a large data set, and usually overinflates the posterior uncertainties. And with the corrections, then the rate of negligible epsilon is increased to a more practical rate. And now with a good enough Monte Carlo that we can estimate ABC, we can implement ABC accurately and efficiently. So our suggestion is that the regression correction should be used with ABC routinely. Yes. So that's all of my talk.
Can I ask one thing about the regression correction?
Mm-hmm.
In your example, you turn a bimodal thing into a unimodal
Yes.
posterior, which is what we kind of want. Assume if our posterior is kind of bimodal and you happen to have a prior to generate theta so that you accept your posterior ABC such that it's kind of unimodal. Does this run into a problem with your regression correction?
So yeah, that's so the issue of those, if your posterior is bimodal, so there are several possibilities. One is that the binding function of your S is not, the value of S is not unique at your two parameters. Okay, so your summaries can, as your data increase to infinity, your summaries could converge to two values. So can converge to the two parameter values. That's which makes your posterior has bimodal. Another possibility is your data size is not large enough, so that makes it bimodal. So the asymptotically, as you get more and more data size, you will push the bimodal to become unimodal, which does make it work. So in practice, it's possible, but there is a paper by David Knott shows that even in multimodal cases, the regression correction still work. Yeah.
Any other questions? Or either speaker, since we have a few minutes. I was just going to ask if, just do any of these stuff to do with knowing the asymptotic rate about how your epsilons should change? Do they tell you anything kind of practically about how you should choose them given any particular?
So the practicality from the result we got is that a good way of learning the proposal is important, because like say we have MCMC and after iterations you can the proposal is kind of from the posterior, and then you just construct the epsilon using the fixing the acceptance probability. Okay, and then this will make the epsilon fall into the negligible region in the asymptotic result. And for other Monte Carlo algorithms that like adaptive importance sampling, is that you iteratively learn the proposals that at some stage, as long as there's not two words, that if the epsilon you get can still fall in this negligible region. So what we try to suggest is that you should learn the proposal. The learning the proposal is important. And also the part of the post-hoc is about the Monte Carlo errors when you use importance sampling. You propose something different from the priors. And the post-hoc is mentioned that the importance sampling variance doesn't really matter much. So, which makes the adaptive learning way of proposal learning way that can work theoretically.
Do we know anything about the non-regular case, super efficient?
I didn't see any super efficient case here.
Do you think any of this would work?
What do you mean by super efficient?
So when efficiency, when the thetas, the mathematical estimator is converging faster than we can.
Oh, okay, that case. Well, in the assumption we assume that so that's possible, because the convergence rate doesn't need to be square root of n. All the result holds for general convergence rate. Holds for as long as summary is converged to has the CLT, no matter what. Yeah.
It's all linked to CLT.
Yeah, it all links to CLT. So as long as you have CLT, it's fine. But if that is not the case, then yeah.
Well, thanks again, Wentao. So I think, as Christoph said, we have our photo now.